So with no further ado, we have four major sections today: material, design, good things to know about incorporating polyethylene into your utility or into your standard repertoire of pipeline materials. And then if we have time at the end, Alan Ambler will go through the methods. Remember, if you need a PDH or a CEU, do what Dan asked, wait till the end, fill out the 2-question survey and say that you want a PDH, and we will send it to you within the next 2 weeks. All right, Matt Hahn, why don't you come on and let's talk about some material, and I'll fade off into the background.
Sounds like a plan. Sounds like a plan. So when we start this discussion, I like to give a background as to where polyethylene comes from, so that we can get into some of the features and benefits of the material itself. So polyethylene is made from a process from gathered natural gas. So natural gas will be pumped from the earth, and then it comes in a form of like ethane-rich gas that has to be distilled. And from that distillation process, you'll get a whole bunch of various products, one of which is ethylene-rich gas. When we crack the ethylene-rich gas, we get pure ethane gas. And that's important because when we add catalyst to that in a reactor scenario, you're going to have a reaction known as polymerization. And so that produces this wet fluff takeoff. That fluff takeoff gets separated into the polyethylene elements and then pelletized. That stuff gets put into a rail car and transported to various converters like Performance Pipe and WL Plastics. We, as converters, then take those pellets from our silos, pump it to the extrusion line where we make the pipe. And that same pipe was used in that natural gas gathering system. So it kind of comes full cycle. Next slide. So when we get it at the plant, we distribute it to our various extrusion lines. And I like to talk about, the process of extrusion real quick, because it kind of gives you a frame set for how the pipe is made and what kind of benefits that'll have down the line. So it comes out of an extruder in a melted extrude that goes into a die. And this die, it basically takes this solid bar of molten extrude and it makes it hollow. And then from there, it'll go into a vacuum tank, which is where we set the OD dimension, that outer diameter dimension of the pipe. And that's important because right there, we're kind of freezing the pipe into that shape. It's a hollow shape with a set OD. And from there, based on the rate that we pull it through, the rest of the process is going to dictate the wall thickness. So that wall thickness then translates to a DR where we generate pressure rating and design guidance info. And then we cut it to length for delivery, or whether or not that be into a coiled product or straight sticks. So when we talk about plastics in the piping world, we kind of categorize them into two different versions. You've got thermoplastics or thermoset. Thermoplastics, like polyethylene, are going to be able to be repeatedly softened by heating and then hardened again by cooling, which is what makes the whole extrusion process kind of work in the first place. That process is going to be reversible and repeatable. So that means anything that comes off the line can be reground up and then re-put in as new pellets to continue the process. Now, in our manufacturing settings, we want to be careful to not introduce contaminants, and that way we don't generally introduce recycled materials into like potable water piping, et cetera. The key about that is that the performance properties of the material remain the same. In a thermoset environment, you may be able to heat fuse or create in a process, but the pipe itself has to be cured. And if you were to go and melt it again, you would have to re-cure it to obtain the same material properties. And that's what sets them apart. So that leads us into the idea of fusion. That thermoplastic nature of the material allows us to take two ends, which this little cross section here is a nice representation of that butt fusion. The two ends were fused down to each other in this case, normally across to each other. And then we've just cut it across to show you this boundary layer between the two surfaces. And that boundary layer is an area that we like to call the co-crystallization zone, or I forget the word we use, a plane of co-crystallization. And so not any process can be used to make a sound fusion. In this case, you have to follow a process that keeps the materials to the optimal condition to make that secure, strong as bond between the two joints. And so just looking at the process right here, we have two pipe ends that were pressed up to a heater plate to develop that molten surface. They removed the heater plate in this process, and then those two molten ends of pipe get pressed together, and we're going to watch it bead roll back. Look at that. So, and then it gets held into this position under a constant kind of pressure load generated by the molten material itself for a period of time that allows the pipe. What happens is you've got these two areas. Let's stay on that slide, please, real quick. So these two blue and red sections represent the two ends of pipe that you're going to bring together. So in the melted state, go to the next one, you're going to relax those crystalline structures within the polyethylene, and you're going to bring them together. As they cool, those intertwined loosened particles are allowed to kind of intermingle between each other. And then as they continue to harden, they're going to recrystallize, making essentially the same two materials whole again as one monolithic structure. And so that's why you're going to have that replicated strength in a heat fusion joint as the rest of the pipe. So polyethylene itself is a semi-crystalline structure. That means there's various regions that are crystalline and various regions that are amorphous that kind of make up the total microstructure of the product. And so what's important about having these two different reasons is that the properties that those instill generate different performance values, whether that's tensile strength or stiffness, chemical resistance, permeability, durability. There's a whole lot of characteristics that can be derived from that crystalline structure, that semi-crystalline structure. Next slide. So as a semi-crystalline polymer, it's kind of eternally within the operating conditions that we have for pipe usage. It's in a rubbery, more ductile state, which translates to better toughness, higher impact resistance, and resistance to rapid crack propagation. So when you compare it to amorphous polymer, something like a PVC, et cetera, when you look at the general operating temperatures and conditions, it remains in this glass-like brittle state, which basically means that it's going to be more susceptible to a fracturing that can be spread down the length of the pipe when it exceeds its limits for impact or pressure rating. And so we kind of derive our strengths differently. So again, polyethylene is a viscoelastic material. What that's going to dictate in the material property is based on the duration of load, it can handle a different magnitude of load. So I like to look at the silly putty model. Stay on this slide if you don't mind. And with a ball of silly putty, I don't know if anybody's played with it, but you can take a ball and you can throw it against the wall and it'll spring back like a rubber ball. But if, return to the previous slide again. But if you were to pull it slowly over a duration of period, it's just going to stretch, stretch, and stretch. So what that equates to in physical properties, these instantaneous durations of load, that's going to be representative of like a surge magnitude. So if you have a surge that happens because of a shutting of a valve, instantaneous, you're going to get an instantaneous spike. And so your material is going to be able to handle that. Whereas if you've got a 50-year burial load, you don't need to resist as much strength because you've got the soil present to help give the pipe support. But then you also have everything in between. You may have a short-term load or a 10-hour load that could be useful when you're evaluating, bending or say pressure testing or installation loads. So these are things that you're going to break into your design when you're going to design your installations. So viscoelastic behavior, basically the silly putty model is if you apply or you hold a stress on the pipe, it's going to continue to deform without any limit. Whereas one of the benefits I like to promote is the stress relaxation model, where essentially if you, in a buried pipe scenario, if you were to apply a deflection to a point where the soil surrounding that product isn't going to allow the pipe to deflect anymore, you're going to relax all of that stress that may have been induced from that burial over time, giving you the longer life. Yes, Alan.
Hey, Matt. Yeah, I'm so glad that you're mentioning this. So that soil interface, when we look at its interaction with high density polyethylene in an open cut installation method, actually supports that entire pipe, just like you mentioned. Now, it's important to note HDPE is considered to be a flexible pipe material, and so does PVC and ductile. So all three of those interact with that soil strength that's around it to be able to make sure any loads that are put on top of that pipe are deflected through the soil surrounding it. So definitely a good synopsis of viscoelastic behavior, Matt, and keep going, man. Way to go.
Excellent. So here's an example. We'll play this video real quick of one of those examples of viscoelastic behavioral reaction. And so this pipe is, if you look closely, you can see that it's actually being dragged along this road surface. Maybe not necessarily something we recommend. You probably want to protect it from abrasion, but I mean, that just speaks to its robust nature. It's making this turn around a 90-degree curve with no real damage to the product because it has that viscoelastic response to those stresses. And likewise, this bucket that's holding the pipe into the air, that'll allow you to temporarily feed it into the hole for a horizontal directional drill or other kind of installation methods. So when we look at polyethylene material, we generally classify them by material designation, or when you get into more detail into the cell classification. These are important figures for when you're specifying a product. I think PPI's MAB number 03 is a model specification. I believe the engineer's package also has model specifications that can help outline exactly what material requirements you would have on the pipe material. But what you can take from this is that gets printed on the side of the pipe, or at least the material designation will get printed onto the side of the pipe, so that inspectors out in the field can verify, yes, this is indeed material that was stated for this application. We're good to go. It's important to specify the right resin grade, because this is going to make sure you're getting the most up-to-date resins for your application. So each of the digits of that material designation are going to represent a material property. First being density, which has to do with material properties like tensile strength and abrasion resistance, et cetera. The second digit you see is the slow crack growth resistance. And I like to talk about slow crack growth here in a bit, but essentially we'll get into the evolution that has come over the existence of polyethylene and piping materials. And then the last equates to pressure rating. So the hydrostatic design stress is what we use to calculate our pressure rating for an environment. And so it's broken up into hundreds of PSI. But just note that the current standard is going to be 1,000 PSI HDS. And I think Dusty or somebody talks about it later in the presentation. So let's talk about some of the resin advances. So over the years, from its first inception back in 1959 was, I think, the first reported installation of polyethylene pipe. We may have had a material designated a PE 1404. Well, over the years, those properties have just improved, because as technologies go on and infrastructure requirements increase, the properties of the material have been evolved to account for those. So whether that's higher hydrostatic design stress to account for thinner walled pipe meeting higher pressure ratings, or maybe it accounts for insulation methods requiring a little bit more precision to withstand the environments that they get installed in. That's the kind of improvements that you'll see by that chart. Yes, Alan.
Necessity is the mother of innovation, Matt. So you're definitely right. It's very important to note that polyethylene is used for lots and lots and lots of different products with different product needs. So the municipal pipe that's sold is a very different product than what they make the milk jugs or the plastic bags out of. And that's part of the evolution that we've seen in the resin. So when Matt talks about a low slump resin, now we're going to do much larger pipe to much thicker wall thicknesses. So the industry itself is fairly excited about this new development, and we're going to be out there putting in larger pipe for transmission mains and other things. Keep going, Matt. Way to go.
Absolutely. So when we talk about those larger pipes, so the general problem with the thicker wall is when you're trying to extrude it, you would have this factor called sag or slump. And that's where the resin wants to fall to the low side of that extrusion process. So you'd end up with a thicker wall at the bottom instead of at the top. And so these advancements allow for larger, thicker, which larger pipe is generally going to be thicker, but will now be possible and more common in the market. So moving on. So yeah, so this is where I'll talk about slow crack growth resistance. So in those earlier stages of resin development, it was common for there to be a potential for failure because of high stress concentration. So you would have failures prematurely to the environment because they were kind of unknown method where something creating a high stress point would allow and held at a constant stress over time would allow that product to fracture at a very localized spot. So what the evolution has done is we've taken the standard for this stress crack growth, which I think even, let's see, in the PE 3408s, that 4 in 3408 represented 10 hours of pent. Well, when you look at the 7 in PE 4710, you have a minimum requirement of 500 hours. So that's an order of magnitude, 50 times the level of improvement over those previous generations. Modern PE 4710s have pents all the way up to 10,000 hours. So we basically engineered that situation likely out of the product. Now, that's not to say that we still don't have to take care to follow proper installation processes to avoid rock impingement or bends, but from pressure itself, we're not going to see that as a failure mode.
You know, Matt, people have given me a hard time for talking about failure, and slow crack growth has been a failure mechanism of polyethylene, and the industry engineered it out of the product. That's exactly. Not to say we can't, as you said, point loads still will not cause us an issue because they can cause a localized failure, but we're not going to get a running crack anymore. That to me is extremely exciting. And that's something I want the engineering community to better understand about our product.
Absolutely.
So thanks for sharing that in this deck.
My pleasure. Next slide. All right. So going on to another resin advancement. So chlorine is an oxidizer, and it's used to neutralize viruses and bacteria within potable water. And so they introduce similar disinfectants, chlorine included, in a primary disinfection at treatment plants. So when we get all this nasty water pumped to a potable water treatment plant, they disinfect it, and then they send it out to their water distribution system. Well, in order to guarantee that no new viruses or bacteria make their way into the water, we included a secondary disinfectant. And that way there's a residual within that water system that keeps it safe for consumption all the way out to the furthest end user. And so the EPA has limits. They've got a maximum and a minimum that they need to be set. But what the fine folks at PPI, with the help of JANA Labs research, they developed a model which allows for us to evaluate your municipalities or your water systems situation to make sure that that residual chlorine or disinfectant isn't going to affect your potable water system. And so the model, what it does is it takes into account different conditions from the average annual water temperature to the operating conditions that you may be in, to the water quality, which could be the residual chlorine. The residual chlorine. It could be the pH of the water. Then also size. So if you've got a larger pipe, you're going to probably be less affected. So the smaller you get, the more sensitive that pipe product is going to be to the exposure. And so we want to be able to evaluate everybody's conditions. So when you go to the next slide, we can look at, based on this PDI index, we can look at the effect of an average kind of environment for chlorine exposure within a potable water to a more aggressive one in various degrees. And the thing that we'll note here, so looking at the average column, that first column, you've got a pretty cool temperature, you've got a fairly neutral pH, and a pretty moderate residual disinfectant total, and a pretty common working pressure, which most, I think 80% of potable water systems are run off of hydrostatic from water towers. So that's going to run generally around 70 PSI because of the height of those towers. And that 4-inch represents one of the furthest out examples that you would have in that distribution system. So with these values and the older generation, that CC2, the CC rating of a pipe goes from 0 to 3. So that older generation of pipe would have a PDI in that average case of greater than 100 years of predicted oxidative resistance. Alan, do you have more to add there?
Absolutely. So just summon straight back to the beginning that you mentioned, Matt. When the municipality uses the EPA established maximum and minimum, you have absolutely no denigration to the Hdpe itself. When we want to use the equations, that's when we're getting out of that maximum minimum for whatever your use is. And remember, some of these equations were not necessarily developed for the municipal potable water industry. They are for other industrial applications as well that drive some of that. And the use of chlorine dioxide as a primary disinfectant also should be looked at. So the difference between primary and secondary disinfectant is the primary disinfectant is at the treatment plant, secondary is within that pipe network. So Matt, you're definitely right on the money. Just wanted to reinforce that one point home. In between that EPA max and minimum, we are good to go. No issue.
So I'd like to ask Dusty Langston to come on. He and I have addressed the issue of chlorine dioxide and failures in polyethylene service lines in the West. Dusty, are you available?
I sure am. Just answering questions on here.
Yeah. Would you mind addressing first, the other plastic pipe people love to complain and suggest that polyethylene fails in the presence of chlorine. We just learned from Matt that it doesn't. Can you give us a practical example of what happened out in the West 10 years ago and how the industry solved for it?
Yeah, so we've actually done a really good job the last couple of years educating on these facts, because I actually get these questions very rarely. Here about 5 years ago, this is all that people would talk about is, HDPE pipe and chlorine don't mix. And so it's really been good the last couple of years that people are getting educated and understanding that HDPE pipe is very chlorine resistant. So about 5-8 years ago, we were having tubing size failures from high temperature and high chlorine concentrations in the Southwest desert. So Tucson, Arizona, Las Vegas, Nevada, and all of these were on tubing for water service sizes. Mostly 1-inch DR11, 3/4-inch DR11, very thin pipe walls. And we were seeing these failures as soon as 15 to 25 years after installation. And so looking at those failures and what the failure method was, which was ultimately sped up slow crack growth, we figured out a way to design for it. And the resins now are all CC3, chlorine categorization 3, which is the highest chlorine resistance possible. And we have eliminated this as a failure method for even the small tubing sizes. So as Matt showed earlier, we have even the very small sizes as a CC3, even high temperatures, high chlorine up to 4 parts per million, you still get that 100-year service life. Anything outside of the tubing sizes, chlorine's really not been an issue in the past. Very, very rare failures on the larger pipe sizes, just because you do have that wall thickness to support the pipe and pressure. But that's kind of the history of where we were seeing the failures, and where kind of some of those rumors about polyethylene not handling chlorine came from.
Well,
But
thanks
again,
for bringing that up. And we also have the data from the UKWIR from 2 years ago, Dusty, that shows that first and second generation polyethylene after 50 years in service still tested in excess of over 100 years. And we can prove that out. I have, Dusty, one additional question. Matt, I'm sorry to delay you. I'm just reminded of this. We also had a person, Dusty, ask the question about chlorine dioxide. What is our recommendation if a utility is using chlorine dioxide as a secondary disinfectant?
And that's a big distinguishing factor here. So secondary versus primary. Primary inside the water treatment plant, chlorine dioxide is completely okay just because it is consumed very quickly in that process. There's not a lot of trace or any trace usually of chlorine dioxide once it hits the pipelines. But if you are using it for secondary disinfecting, we're not recommending polyethylene. If you have something that is maybe like a closed loop system, part of your process of the water processing plant, maybe we can work with it. But usually in a full-on distribution system, if you're using chlorine dioxide, we don't recommend using polyethylene.
Right. And it eats up gaskets of other materials. It's also,
well, it eats everything. It eats metallics, it eats fittings. Chlorine dioxide is super aggressive.
Yeah, Water
So,
Research
Pete,
Foundation.
I'm going to interject in this moment with that exactly. So all the disinfectants there are oxidizers. They are intended to release those electrons. That's what they're supposed to do. Varying levels of that disinfectant. We've got a lot of great questions about it, so I'll just spend a couple of seconds on it. Chloramines are a lower disinfectant. They are put in through secondary disinfectant in the pipe networks. There is some material out there that show that they can be aggressive to gaskets in a bell and spigot gasketed system. Liquid chlorine is the next one up. Remember, chlorine dioxide or chlorine as a gas, which used to be used and is not used much anymore, are very aggressive oxidizers that are actually potentially very dangerous as well. So at the treatment plant, they have to handle them, and that's what they're intended to do. So we've got a lot of questions, guys. This is exactly what we're looking for in a 301 like this in a dynamic format. So please keep sending those questions through. And when we start to see a whole lot rolling in on the differences of what we're discussing, we will pull the full team together to do exactly what you saw. So keep going, guys. Thank you very much.
Absolutely. So when we talk about our temperature operating range for polyethylene, we're a little less concerned about freezing temperatures than many other piping materials, because water can freeze within HDPE without causing any damage to the product. Part of that, if you don't mind hitting the next slide, is do it again until we fill those up. So it is again based on that brittle ductile temperature. So every time you go below zero all the way out to -130, we're not even getting into that glass phase of polyethylene. So we're still concerned about impact damage, the potential that it may have to the product. But when we're talking about water freezing, it's not generally encompassing impact to cause any detriment to the polyethylene itself. So we've also mentioned that polyethylene is a heat fuse product, which ventures into a leak-free environment. Other products out there may have to address those issues with regard to leak, but the only kind of concern over leakage of water that you're going to encounter in a properly heat fuse system is going to be based on third-party impact. And so when we start talking about other materials like metallics, we have to bring up the concept of corrosion and tuberculation. So polyethylene doesn't rust, rot, corrode, tuberculate, or cause or support biological growth. Pardon me. And so that's one of my favorite expressions regarding the product itself, because we don't deal with this type of phenomenon in that environment. So the problem with the different methods of corrosion on metallic pipes is that they can lead to tuberculation, or tuberculation can lead to them, where you're getting a constriction on the flow, or the velocity may increase within the pipe, which is a little more volatile when you're dealing with pressures and stresses on the material itself. So polyethylene itself is a self-restrained product. So that means you don't have the bell and spigot connection. So you're not worried about separation in the same situation. In this particular picture, we have a washout of what I believe was a firewater main for a mining operation. You can see the gentleman on the hill looking at this may be an extreme example of what could happen, but this pipe itself remained in service while they were able to finish work and save guys down in the mine situation. This is one of the benefits of the pipe. It demonstrates its flexibility and durability. We often show you the images of people taking their fine automobiles out underneath the polyethylene pipe string. Here we have a Ferrari not getting the memo that he needed to evacuate before the installation. But the
Matt,
picture
it looked
on the,
like that guy really did trust the viscoelastic behavior of HDPE pipe there.
I'm not sure I want to go out under there, but I mean, it made the trip. That picture on the right is one that I love to promote because we are a self-restrained system. We're not having to introduce fittings to make a tight diameter turn, where in a bell and spigot situation, you're worried about deflection at those joints and those interfaces. So you have to keep the pipe relatively very straight. With polyethylene, we get to bend it and flex it around, even in the final installation. Dusty, do you have something to add?
Yeah, I just like to show on that picture. Standard 40-foot cul-de-sac, you can actually wrap a 8-inch DR11 standard, water distribution pipe completely around that cul-de-sac with zero fittings, zero directional change fittings. So you can go in and out of that cul-de-sac with an 8-inch main and not have to use any directional changing fittings.
Yeah, and I think that picture also brings in a fusible PVC where it was nearly, 20 times as large a bending radius requirement on the material. And that brings us to this slide. The bending limit is going to be based on the wall strain that we would recommend you keep the pipe above. So this is in a final installation method. So this is a long-term bending limit, but we limit it to a 2% longitudinal wall strain, which equates to the thickest wall pipe, a 20 times OD kind of ratio. For thinner walls, we have to take into account that the resistance to kinking is going to go down. And so we want to be wary of, I think this pipe that we're showing in the picture that kinked was maybe a DR21 or thinner pipe that we just kind of over embellished what we could run it to, and it failed in a kink method.
Yeah, I actually think that was a 32.5, so it's even thinner.
Oh, even thinner. There you go.
Yeah, it was a very thin one, and they were trying to bring it around to an insertion pit, and yeah, it was just too sharp of a turn.
So what happens in these situations in the field, and this is part of the viscoelastic durable behavior, is if you get a kink like that, you just cut it out and refuse it.
Yeah,
and
they would have lost about 1.5 feet of pipe there due to that kink, and they would have just cut it out and fused it back together.
Yeah, not a major
30
loss
minutes
there. Yeah, exactly.
Guys, we have 45 minutes left, and Alan and Dusty, I'd like to ask you guys, we've had this question 3 times already today, and that is, how long can you dose? I mean, Matt talked, Alan, about a residual chlorine. He didn't talk about the dosing of chlorine and cleaning that pipe before you put it in service. How long can we expose polyethylene to a 20% chlorine solution during disinfection?
That was for me or for Alan?
No, you guys decide.
Oh, sweet.
Go ahead, Dusty.
Absolutely. So I get this question all the time. Hey, had a contractor, we pre-chlorinated a drill string, and we came back a month later and we forgot to drain it. So it's had chlorine in it for a month now, out in the Florida temperatures, high temperatures. Is that okay? Has it done any damage? And the answer is ultimately no. You have to look at the way chlorine actually affects HDPE pipe, and it has to have a force behind it to cause that reaction for chlorine to degrade polyethylene. And so when you just have a pipe full of a chlorine solution, there's nothing there. There's no force there that's actually of creating that reaction. And so if you had that drill string fully pressurized and chlorined that whole time, then we'd actually have to look at it. We can take samples and we can figure something out. But most of the time when you're doing a chlorine test, you don't have it under pressure. You've just filled the pipe up with your chlorinated water and it's just sitting there. So in those times, nope, there's no issue at all.
So the routine operating parameters to which we would flush a pipe with superchlorinated water. So this is levels above that 4 milligrams per liter that EPA recommends, are when we're trying to tie that new pipe into the pipe network system. So in that situation, let's use a horizontal directional drill or pipe bursting as we're pulling in a string of pipe. We would basically put a pig into one side, and in front of that pig, we're going to put chlorine pellets or liquid chlorine or some other type of disinfectant on the front, and then tie that pipe into a valve network as to which we would open up the valve, flush that water through, and pour out any other debris that may have entered the pipe. Once that's done, that pig comes out, everything's out of that new pipe, then that superchlorinated water is also out of the new pipe. We're going to dechlorinate it, of course, on the other side as we're collecting it through, but now you have a nicely disinfected brand new pipe system to pull in. That is the majority situation as to which a pipe will experience higher levels of chlorine. Dusty, of course, explained the minority situation of the oops, hey, look, I got to see it in this scenario. In all cases, we certainly don't want that huge amount of superchlorinated water just for safety of those people that may very well consume it as well. So, Matt, you got something else?
No, I was just going to allude that we'll pass it over to you for the next portion.
Yeah, great job, Matt. Thank you. Alan, you're up.
Okay, so here we want to talk about pressure rating for the pipeline itself. So engineers ultimately are very conservative people. So even though we've shown you that the majority of pipe networks throughout the country for potable water operate between 55 and 70 PSI, the industry itself has asked for what's called a DR11 pipe. And a DR11 is a 200 PSI working pressure pipe. So on top of the 55 to 70 PSI, we have that difference in operating pressure, but we also have conservancy on top of that built into the high-density polyethylene. So some of you had asked about, and again, thank you so much for the questions. It makes these all so much better. Pressure rating in higher temperatures. There is a temperature compensating factor. There is also a factor as to which we would derate the pipe if there was presence of hydrocarbons or other things that you would put through there. So we understand with equations defined how we would derate the pipe in particular applications, because you're not always going to have you might have an above ground pipe that's going to experience high temperatures as to which we show. So here's just some common ratings for you. In reality, engineers don't always need that extra line of conservancy, but DR11 is what is mainly used for potable water. So go ahead and advance. So surge, we show through the design of the pipe material and proven from the hydrostatic design basis that Matt had mentioned. They're actually blowing up the pipe, seeing when it fails. These are much, much higher pressures than what we actually see in operating scenarios to be able to establish that graph of hydrostatic design basis. And then on top of that, they're allowing surge pressures. So the surge activities that happen day to day in a potable water system, if you want to advance to the next slide, are going to be pumps on, pumps off. If you have variable speed drive pumps, those obviously mitigate that surge a little bit as well. Or if you close the valve, open the valve, maybe too quickly, that type of thing. So you'll see water hammer that occurs within the pipe. It'll also represent an increased surge through it. We want to account to make sure that over time, that change in surge and water velocity is absorbed within the pipe. So it doesn't lead to fatigue. That 1.5 times the operating pressure for 200 PSI is at 300 PSI. So now the occasional surge event is up to 55 times a day of change. So our 55 to 70 PSI water system now has 200 operating, now has 300 at 55 times a day, and then a handful of times a day at the occasional surge, which is 400 PSI. So we're seeing a huge amount of conservancy right in that. So if you're looking for belt and suspenders, this is definitely 2 belts and 2 sets of suspenders on top of that for you. That change in viscoelastic behavior and that modulus of elasticity actually is lower than the other 2 competing pipe materials, being PVC and ductile iron, but it allows us the opportunity to attenuate that surge. So there's less actual pressure increase with a higher velocity change within HDPE. What's interesting and confusing for a lot is to the way that these are actually calculated at AWWA. All 3 assume different pressures and ways to be able to measure the pressure class. So here HDPE provides that 1.5 times and 2 times that pressure class within the actual design of the pipe. PVC, the recurring surge, has to be designed in the pressure class of the pipe that they're recommending, and then also the occasional 1.6 times that. And ductile iron is limited to that 100 PSI. So they often try to keep the velocities a little bit lower in that 2.5 feet per second range from what we're looking at within the flow of the pipe. So go ahead and advance. So again, I mentioned cyclic fatigue. So over the lifetime of that pipe, when we have those surge changes, as we're predicting the lifespan of the pipe, that's where that cyclic fatigue comes in. Matt had mentioned semicrystalline and amorphous regions. Those now in the 4th generation of poly have been designed to address that cyclic fatigue. There are calculators available to you online, PPI's PACE, that'll let you make some assumptions and enter into those values that are right there in order to be able to spit out results and comparison directly between pressure classes of ductile iron, PVC, and HDPE. Go ahead and advance. So over time, as Matt had seen and shown, corrosion happens within the interior of the pipe itself. HDPE does not corrode. That friction factor is maintained through the entire life of the pipe. So we are not going to experience a reduction in flow capacity over that time period. It's an interesting argument to make within a pipe network that you would have to have the ID of an HDPE pipe exactly match that of a competing PVC or ductile iron pipe in that manner. Velocities may increase through a section if that ID is smaller, since we're achieving a higher pressure rating through the HDPE itself, but then the velocity will increase there. The absence of lots of fittings from 22 degree and under bends that have to be inserted into a bell and spigot system is saving us massive friction factor through a complicated network. Only in the extremely idealized long pipe run, one source, no connections, would we really want to look at that friction factor as we go through this. So very interesting to see the flow through a pipeline in this situation in these pipes as we compare it as well. We did get asked about permeation. So all that high density polyethylene is from a molecular level is molecules of hydrogen and carbon with a little bit of additives that they put into it at the manufacturing facility. It does allow those similar BTEXs or complexes of hydrogen carbon to pass through the wall. We really want to look at these scenarios when we have stagnant water within a pipe that's simply not moving in a brownfield area. Now, from an environmental engineering standpoint, if we know we have a brownfield, no matter what, the best result would be to renovate or decontaminate the brownfield, remove the soil, remove the pollution plume, and then put some pipe back, or put the pipe in a different location. Now, in bell and spigot systems, that brownfield will also permeate through the bell and spigot as we go through. Dusty, you want to add some?
Yeah, love talking about this topic. We often get the question, like you said, is HDPE pipe permeable? And you hit it right on the head. Yes, it is. HDPE pipe is the most commonly used pipe material in the oil field for oil and gas gathering. And so even though it is permeable, we understand the effects, we understand how to design for it, and it's the main pipe for actually conveying gas and diesel and oil products. As Alan said, if there's ever a time that you think you're going through a brownfield or an area known to have hydrocarbons in the soil, obviously best to avoid it. Can we go around? Can we go under it? Directional drill through that section. If we can't, dual containment pipe is a great option if you have to go through it. Another option is remove the contaminated soils, and then whatever you put back on top of the pipe, bring in clean, non-native backfill. And then there's also manufacturers that make a polyamide, a nylon pipe wrap. Very similar to what you would use for a ductile iron pipeline. Using a polyethylene pipe wrap, you could use a nylon pipe wrap for polyethylene, or any bell and spigot jointed pipe for that matter, to make sure that you don't get that hydrocarbon permeation into gaskets or pipe.
So Dusty, is it true, Dusty, that they use polyethylene to wrap ductile iron?
Yeah, yes, it is. Yeah, they're Bio V Max, or I can't remember their product.
Could you imagine if we came? Could you imagine if we came to this audience today and said, "Hey, use our product, but wrap it in ductile iron"?
You're right. Yeah, always. Sorry, Alan. I'll let you go back to it.
Alan, you there?
Yeah. I was going to say, Dusty, you keep going. Give me a couple minutes to answer a few questions.
More than happy to do that. So as we mentioned earlier, the pipe is fully restrained because of those fusion joints. Whenever you have a fully restrained pipe system, you have to take in consideration Poisson effect. This is steel pipe. This is any kind of pipe that is welded together into a pipe string. And so if you pressurize something and it expands circumferentially, it's going to want to shorten lengthwise. And so it's important to restrain that pipe if you transition to another material to avoid, pull out, for example, of the polyethylene pipe. My favorite example of this is directionally drilling HDPE pipe under a roadway, under a river, and then transitioning back to maybe a ductile iron or PVC or something like that after the drill string. And if you were to just purely insert the HDPE pipe into the bell of a ductile iron pipe, once you pressurize the polyethylene, it could shorten enough to pull out of that bell. And so it becomes very important for the ends of the drill string to restrain those transitions. There are lots of mechanical restraint options, bolted options, MJ adapters, mega lugs, things like that. But if you purely rely on that, you're going to have to worry about the joints further down the line that are also unrestrained of bell and spigot jointed pipe. And so the best thing to do is just pour thrust block at the transition point to hold that drill string or that length of polyethylene still and keep it from wanting to move. Alan, go ahead and back up. That was a great slide you were just going through, showing that with HDPE pipe, there is no thrust blocking when it comes to directional changes, when it comes to Ys, Ts, elbows, anything like that. There's no need for any thrust blocking for HDPE pipe. It is purely when transitioning to another unrestrained pipe system that's not polyethylene. And you can see there the fused in wall anchors, or you can use these electrofusion restraint collars. If you were to pour concrete thrust block straight onto a smooth polyethylene pipe, there's no grip there. There's nothing for the concrete to hold on to. And so the HDPE pipe can actually move within the thrust block. So either casting a wall anchor or several electrofusion restraint collars into that thrust block will hold that polyethylene pipe still. I personally love the electrofusion restraint collars just because you don't have to worry so much about placement because you can put the entire installation in the ground, and then you can install those electric fusion restraint collars, or as my daughter calls them, princess crown collars, into, you put them wherever you want, and then pour your thrust block around them. Yep, and here we have a setup. They're ready to pour thrust block as they transition. And this is a beautiful transition. I actually answered somebody's question earlier. How do you transition from polyethylene to PVC? And I said, predominantly use our MJ adapters, mechanical joint adapters, and they transition to a valve in between the two pipe materials. And this is exactly what we see here. This is an MJ adapter being installed into a ductile iron valve. You can get polyethylene fully welded ball valves, but if you want to continue using standard ductile iron valves, this is how you would connect them. There's a company called AVK that actually has ductile iron valves with polyethylene stub ends on both sides, so you can weld up to them instead of having to do a bolted mechanical joint.
So Dusty, here's a video that thanks to Dan Landy's our most popular video on YouTube. And this is a demonstration of putting in a polyethylene spool piece to connect to an existing PVC line. And you see here the crew, Dusty, is working on getting the concrete out because there was a change in direction. So we're going to replace that T with a new ductile iron T after we get through with the concrete. And while this guy's doing that, there's a guy at grade building his polyethylene spool piece, getting it ready, Dusty, with 2 MJ adapters that we'll see momentarily.
Yeah,
so here's that
particular case. This was a failed fitting that was leaking, and so they had to cut out this PVC and ductile iron combination, and we're going to replace it with polyethylene.
Right. So eventually, we're going to put in our spool piece, or about a 10-foot polyethylene spool piece, and we're going to connect it to that T. Now, Dusty, we're working on creating the spool. So this is what is the best practice for polyethylene connections to legacy materials. So right here is the gentleman's building the spool, and you'll notice there's a mechanical joint adapter on both ends. On the right-hand side, we see it has an insert stiffener in it. That's that metal piece on the right there, Dusty. Why do we need an insert stiffener?
Yep. So anytime you have an external compression force on polyethylene, this can be an external coupler or an MJ adapter. There needs to be something to fight that stress. Anybody who's familiar with house plumbing and plumbing water lines with PEX does the exact same thing. You have to have that insert stiffener for the external force to be able to clamp down against and create a permanent force. There are some companies out there that can get away from this by using thicker gaskets for coupler manufacturers, but most of the time we still recommend using an insert stiffener to give something for that compression to bite against, and so that it won't creep away from that stress over time.
So this is a pipe bursting job. So they're running east-west now into that PVC line, Dusty, and they're going to run a 400-foot pipe burst and connect up to this valve. And they were using the mechanical joint adapter. I love this video because it shows not only what an MJ is, but also how to connect it. And on those kits that you can buy, it actually comes with that gasket as well. So
that's correct.
Yeah,
yep. And that insert stiffener, you don't need to worry about that as a field guy. All of that comes fully installed and ready to go. All he's doing there is he actually removed the gasket to clean it and put it back on. They've come fully built that way, and you just fuse it onto your Hdpe pipe on the other end. Moving on for thermal effects, if you do have an installation that's above ground, it's great to kind of snake that back and forth above ground so that you don't get localized movement. As the pipe heats up, it will attempt to grow if you don't restrain it. We've had cases up in Wyoming, up in the oil fields where, they don't actually bury this pipe. They leave most of it above ground. They install it in the winter, come back in the summertime, and it's walked out, possibly into a roadway or some kind of crossing. So it's best if you're doing an above ground application that's just out in the sticks, weave it in and out through trees, for example, or rocks, and use those kind of as lateral deflection limiters. And you can also fully restrain and actually anchor the pipe if you want, but expansion loops are rarely ever needed. Thermal expansion, this is a constant. Polyethylene pipe does grow and shrink with temperature. All pipe materials do, but when you're using typical bell and spigot joining methods, that pipe is actually expanding, contracting within the bell. So you never notice. When it comes to steel pipe and polyethylene pipe, that's a welded pipe system, you're going to notice if there is expansion contraction. And so while HDPE pipe, you look at this situation, 2-inch DR11, 200 feet of pipe above ground with a 40 degree temperature change, it's going to want to grow or shrink 8 inches. That seems like a lot. Steel under the exact same situation is only 3/5 of an inch of growth or contraction. But the thing to pay attention to here is it only takes 320 pounds of force to actually stop that HDPE pipe from wanting to move. So it's very, very easy to fully restrain versus a steel pipe.
Yeah, great job. Thank you for filling in there for Alan, Dusty. He's got his hands full on questions. Believe it or not, we've had over 62 questions already. We have 30 minutes to go, and we've lost maybe, Dusty, 3 people. We have 2 more sections to go. Right now, we're going to do things to know. Chris Waite asked me to include the data logger. And the reason we like to talk about the data logger is because it gives the engineer, Dusty, the confidence to know that when they're not looking, the operator's doing what he or she is supposed to be doing. It's a minimal cost to add to the job, and it provides so much to a good spec, to good training, to proof that the tech has been trained as he or she should have been trained, and add that to testing. It becomes a pretty fantastic system. And the only thing then we really worry about is third-party damage, as long as the fusions have been done correctly. So this is a device that connects into the hydraulics of a piece of McElroy machinery, and it reads the hydraulics and the pressure over time. And it gives the engineer at the end of the process the knowledge to know that that joint that individual did is good or bad. So here's what the operator sees on his screen as he's conducting the fusion. So he can follow pressure over time on that graph, and then you overlay it with a colored chart and say, hey, did I follow the rules like I was supposed to? Let's dive. Typically, all we show is this. We're going to spend a couple minutes looking at what that operator sees on his screen as he's doing it. Let's take a closer look. So the data logger itself is ruggedized a word? I guess it is now, but it's a rugged tablet. Think Toughbook on a PC, drop it on concrete and it's going to be fine. It's got a warranty, just like a car, 3 years. It's got a battery. It's hot swappable. Think about that. So you're at the end of the workday, the next operator's coming in, you're going to use the same data logger. You can hot swap it. And it's not going to lose the data. It's got front and rear cameras, and cameras are an important part of what that operator's doing. And it's 5G and Wi-Fi capable. So that engineer, if he didn't get out on the job site that day, contractor says, hey, I want to put these joints in the ground. That engineer that's responsible can be 300 miles away, go online and check those data log joints to make sure that they are okay. So here's what this looks like at the start of your workday. So you're looking at the screen, you hit start, you say, oh, okay, my name's Shannon Land. I'm working on a 28 high force machine. That means it does 2 inches to 8 inches. I take a picture of myself to prove who the person is doing the job. There is accountability by person, by data logger. And we're going to do pipe fusion instead of electrofusion or testing, which are now capable. Yes, I'm going a little bit quick because this section is kind of long, and we've got to get back to Alan. You pick the machine that you're using. It makes a difference. What machine you're using. And it gives you the summary. Are we doing an in-ditch kit? Are we tying in a fitting or not? All these different kinds of fusion. What standard am I using today? This is a little outdated. Our current standard is ASTM F2620-20. So it was updated in 1920. What kind of fusion are we doing today? We're doing butt fusion. And you're saying, oh my God, this guy's got to do this every time. No, this is the initial one of the day. And then the next joint you do, all that same information is saved, and it just gives a new joint number. Then you can take a photos of the good face-off. You can take a photo of the job site. You can take a photo of the machine. The data logger records, hey, what's the temperature outside today? Am I doing an 8-inch IPS or 8-inch DIPS? Oh, I did IPS in the morning. I'm doing 24-inch dips in the afternoon. Who knows? Then you can trace the pipe and put in the pipe data. I'm fusing 8-inch IPS to 8-inch IPS. Therefore, that would be identical pipe. My pressure needs to be 75 PSI per square inch. We're checking for drag. My bead, my heat soak time, my fuse cool pressure, all that pressures, all those different pressures are included on the data logger. I check my heater face to make sure my temperatures are okay. And then I'm ready to start fusion. That's how easy it is. It's fantastic. Thanks for letting me blow through it, but it's so important to accountability. Also on the accountability front, we have another tool that is a destructive test. Back in the day, they used to cut it out and stick it on the back of a vise and test it on the back of that pickup truck. Obviously, that's an unsafe thing to do there on the left, but now we have the McElroy side bend tester that allows you to take a coupon, plane it down, and test that joint. For electrofusion saddles, we have this one, which is ASTM F1055, which permits us to, excuse me, do a destructive test on a saddle to make sure that it was fused correctly. Let's take a look at this one. So what we're trying to do is get it to pop off the pipe. And then if it failed at the stem, we know it was a good joint. If the saddle popped off, we know the operator didn't do what he was supposed to do correctly. So let's look at it in slow motion. All right, so this one broke at the stem. Let's look at that a little bit more closely. So right here is the stem, the smokestack. Here's the saddle, and it ripped off here. Had we not peeled and cleaned properly, that saddle would have popped off under all that stress. Or we can do this highly scientific test with my good friend Steve McDonald from ISCO, where he's banging on this Electrofusion Corporation saddle to prove to an owner who is concerned about using electrofusion. And he loves it when I show this video because he's got that sappy look on his face.
So some of the development of these tests, everybody out there, came from doing the fusion the right way and doing the fusion the wrong way, so we could test whether or not the actual fusion worked. So the operator that would be performing that electrofusion would subsequently not prepare the pipe in the appropriate fit manner, study how it failed, and then also be able to recreate that routinely. So we do have videos that show improper preparation of pipe and electrofusion fittings in that manner to be able to show you what those failures should look like. They aren't part of this presentation, but they are part of the Alliance's vast collection of videos on all things Hdpe. So in the field, you can repair this pipe, and there are multiple ways to do it. So advance all the way to the end of the slide. We'll keep showing you. Mechanical fittings, like everybody that's an operator out there has in your yard already, have been developed to be able to in the middle of the night, slap right on that potable water main when we've got that leak going. The fittings, heavier duty fittings, now are considered to be a permanent repair in some instances, depending upon the quality of the fitting. But then also, if you need to come back, not in the middle of the night, to cut that section out, there are flanged pieces, electrofusion pieces, where we simple measure twice and cut once on the length of that pipe that we're going through and insert a brand new pipe into it. So here's a good picture example of that damaged section being removed. They're measuring twice and cutting once, and then we put 2 electrofusion couplings on the end. Fire those couplings up after properly preparing. We're scraping that pipe and making sure it's inserted in the proper stab depth and everything that we need to be able to come through and do that connection properly to replace that pipe. There's also here more examples of those permanent solutions. and temporary solutions through mechanical fittings. So those operators out in the field that are much more familiar with this, if you have that available to you, then you go through and use that. Now, the quality of the fitting depends on the manufacturer, so you'll have to talk to them to see whether or not they consider that to be a permanent or a temporary repair. But at 2 a.m., most of them are going to get the job done for you. So we're going to cruise right into methods. We have about 20 minutes left. Love the questions that are going. We're well above that 70 question mark. So here, want to talk about that viscoelastic behavior and what Matt Hahn had talked about before with the soil interacting with that pipeline in order to be able to handle the stresses from either live loads, soil loads, surcharge load, or anything that happens that way. The difference between flexible pipes and rigid pipes is exactly what you're seeing on the screen. The soil is meant to interact with that flexible pipe to be able to distribute the loads and make sure that that pipe does not deflect and deform. A rigid pipe, such as a VCP, cast iron, asbestos cement, or pre-stressed concrete cylinder pipe, takes and distributes that force directly to the bottom soil underneath it. So it does consider the soils to be surrounding that pipe significantly weaker. And so the varying DR levels that we have here, DR7 to DR32.5, have a pipe stiffness factor that plays in. There's also a soil stiffness factor that plays in. So both of those things interact. In some instances, you won't really need a heavily compacted soil if your pipe stiffness factor is up where you need. Go ahead, advance to the next one. So here's a schematic that we'll go through essentially of if there was no soil support surrounding that pipe, we go up the stress line, we continue to load that pipe through as we go through, and now we're going to have creep of that pipe as it moves. So if you continue to push on that pipeline, you're going to deform that pipeline over that long time period. If it's a 50-year install, it's obviously very different than the temporary condition when we're moving it in to place or pulling it in through a horizontal directional drill. Now, when we have that surface on the side, the soil interacting with it will go up that stress curve, remove the stress loader as we get through because it's deflected into the soil surrounding that pipeline. So we will not have creep associated with this pipe as the design of the pipe stiffness factor and the soil stiffness factor will work together. Keep going to be able to make sure that we do not deflect that pipe. That's all that this is doing. It does the same for both PVC, ductile iron, and high-density polyethylene sometimes because of the lower modulus of elasticity and durability, flexibility of Hdpe. It's hard for some people to get that wrapped around. So go ahead and go to the next one. What we're looking for in this terminology, those pipe embedment materials, we're resisting that deflection of the pipe, wall buckling for a constrained pipe. So we're looking at all those. Resist allowable external pressure for an unconstrained pipe. So this is going to be in a vacuum scenario. And then we also have to beat that wall buckling. So if you do not want to get into these calculations, which is perfectly understandable, there is a design window for you that'll be on the next page as we go through. Go back to the video, Pete. So I'm looking at this. Pete puts this one on social media, and they just love to try to eat him alive for it. Oh, the pipe doesn't have all the things that it needs to be able to be successful. That's not true. It's got a foundation, which is the undisturbed soil at the bottom. It's got bedding. The bedding itself is not compacted, so it's basically providing a safe spot, a void of rocks or other things to be on the bottom of that. You're not seeing that portion of it, but then there's embedment and backfill that's placed on top of this pipe. This is in a clay native material. It doesn't look like there's going to be a box truck loading on it. One of the reasons why I love to point this video out is the fact that there's nobody in the trench. You don't have to get in there to secure the bell and spigot or make the connection to a valve. Obviously, there'll be a valve, a larger excavation on the other end when we're tying it into place, but it's safer for the employees by not being in the trench in that manner. Next slide. That design window, as we talked about, is DR7 to DR21. Minimum depth of cover with that H20 loading is 3 feet. no H20 loading is 2 feet, and a maximum depth of cover of 25 feet. So that does not necessarily mean that you can't bury it deeper than 25 feet. That means that if you do not want to do any intense open cut excavation calculations and your pipe lives in this window, you do not have to do them. If you want to do them, we've done them for you and have spreadsheets available. So just let us know, send us a Q&A. We'd be happy to be able to give you that, and then you can calculate your little heart away. So here is some trench width that we're looking at. Of course, this standard excavation bucket is already set at some of these trench widths as we're looking for. So that nominal pipe size of 3 to 24 inch, we're looking at that OD plus 12 inches, and 24 inches for nominal pipe size, we're looking at OD plus 24 inches. And what we're looking at for embedment requirements on max particle size, for a 6 to 8 inch pipe, we are looking for a 3/4 inch max particle size. Why I call that one out in particular is oftentimes to stabilize the bottom of a trench when groundwater is present, they'll dump what's called 57 stone. It's called 57 stone because that's what shakes out of a specific sieve, and it is that 3/4 inch and smaller particle size. Stabilizes the bottom of the trench. You can fill up and embed that pipe 6 to 8 inch in that 57 stone with no issues and no problems. But when we get into larger pipes, obviously we're getting into larger particle sizes too. So keep going. This is an open cut lay-in method where the contractor has observed that they can cut very long lengths out in open cut and take advantage of extreme productivity by fusing that long length up in advance. So here they're just taking and putting that pipe right off of the surface directly into the excavation, and they'll come back through and excavate as we move forward. So keep going. HDD, we'll talk a little bit about horizontal directional drill. This is essentially the gateway drug, for lack of a better term, for most municipalities' introduction to horizontal directional drill. And a very brilliant engineer at a municipality, Miami-Dade Water and Sewer, that I've known said, well, hell, if you're going to use it for the difficult thing, why don't we just use it for most things? And that makes perfect logical sense, Louis Ahemil. You're absolutely right. So here's some industry guidelines for you that can help you design your horizontal directional drill. PPI has also created an online guide and bore aid that you can put your lengths, put your entrance and exit angles, everything that you want to look at to be able to make sure you design the project correctly. Most common errors for people that are not familiar with horizontal directional drill are going to give too high of an entrance or an exit angle. We want to keep those limited, typically under 18 degrees for pipe exit, under 15 degrees for pipe entrance in that manner, and that's a limitation of the equipment. That's not a limitation of the HDPE pipe. It's really a limitation of that. So what we are looking for from a design analysis is friction along that bend when we achieve curvature underneath whatever it is we're trying to clear at depth, and then we come back out to achieve that curvature. HDPE as density is lower than water, so it will float. Sometimes we will ballast that pipe by putting water inside the pipe to make sure that we lower those friction forces as we go through. ASTM has a very good standard on this, and ASTT has a great book to give guidance as well, but the Alliance also has spreadsheets. You certainly can send us a note and we'll help you work through your horizontal directional drill specific project and talk to you about it. We love to talk about HDPE, as you're seeing here in the almost 90-minute of a webinar for you. So safe pull force is understood. It is defined within the Plastic Pipe Institute's Handbook on Polyethylene Pipe and some of those other resources I talked to you about. So what we're looking for is that duration of the loading that plays within our modulus of elasticity. Once we start to pull that pipe, we typically don't want to stop that process, and we want to make sure that we are going to not pull past the yield tensile strength of that pipeline itself. So it is calculatable. And again, we do have spreadsheets for it. So essentially, we will drill that pilot hole first. We're going to make sure that we put it, it is an intelligent tool when we're first tracking it. We want to know the location. So you're going to know the depth angle. You're going to know where it is vertically and horizontally to make sure we get the bore path in the appropriate location when we come through. Then we continue to ream once we reach the other side, that hole. Now, a reamer itself is going to just enlarge that opening. They may do it in one swath. They may do it in a couple of passes through it. We're typically going to try to make it 50% larger than that HDPE pipe. The internal part of that hole, of course, is pressurized with drill mud, typically a bentonite with some additives and other things that keep that borehole open and also keep that cuttings that the reamer is going to actually create when we're removing soil or other things that we're cutting through, and it's going to circle that back to the opening of the HDD hole for us. So we had a great question, and I'm sorry for delaying a little bit in answering it live, but the question was, how long can you slip line? If you want to advance to the next slide, Pete, we'll talk a little bit more about slip lining too. In reality, for HDPE, there is no limitation as to the length that you can actually fuse together to find a productive installation. The limitation will be the size of the opening for the pipe, the difference between the ID of the existing pipe and the OD of the replacement pipe, and then the machinery used to be able to put that pipe into place. So you're seeing this video on the right. We're basically putting a 500-foot run in all about 5 minutes by just pushing that pipe through to the inside. Sometimes you'll pull that pipe. It depends on the length and the method for the contractor to be able to come through. But as long as we properly prepare the ID of that existing pipe, do not have any obstructions, we're just going to slide that puppy right in there, and that's going to be a very good rehab for us to go through. Yes, Pete?
We just had a good question. Can you slip line through bends using a slip line method? Slip lining through bends. Can you do 11s? Can you do 22s? How about 45s?
Typically, you're not. Typically, those bends are going to be excavations, as we want to make sure that we're not going to cause any friction on that pipe or get it caught up in some way. Now, you can compare directly the OD of the replacement pipe and the ID of that pipe and look and calculate through the curvature. But a lot of times your contractor is going to say, no, let's just go ahead and do an excavation in that location. If properly prepared, that'll be in a pipe entrance and an exit point as we go through. Compressive fit slip lining only uses high density polyethylene and is fairly amazing knockout technology that's new. We're basically going to push that HDPE through a die where we're going to make its OD smaller. We're going to pull that through. So the material comes somewhere. We're going to lengthen the pipe run that we go through. As we pull that through, that material is going to shrink, and we're going to pull it into an existing pipeline, and then it'll allow to regain its natural shape and push against that ID of the pipe. HDPE can only be used for this. Most of that relaxation occurs, of course, in the 2 to 24 hours surrounding it. So engineers that are conservative, we always want the largest ID we could possibly put back. If you absolutely have to have that, then you would look towards compressive fit slip lining in this application. So the forces, of course, are greater. You're going to have to be able to resist any urge for that machinery to be able to push through the soil column as we go through. Keep going, Pete. So we're going to talk about pipe bursting now. Pipe bursting actually is the only trenchless technology rehabilitation to do replace that pipe with a larger OD. Does 3 things simultaneously at one time. It will fracture the existing pipe and put it into the 2 to 3 inches of soil surrounding your replacement pipe, create a temporary soil cavity to receive that pipe and give you that production pipeline as we go through. Trenchless technologies have been shown to reduce excavation by about 85% in suburban and urban areas. This is unbelievably useful in the fact that we are dramatically reducing the cost, which excavation does quite a bit in that cost. We're restoring that area. The types of pipe that you can burst: cast iron, clay, PVC, concrete. You cannot burst a reinforced concrete pipe or pre-stressed concrete cylinder pipe, anything that has a inner working part together. Asbestos cement pipe is legal to be able to burst. There are regulatory requirements that must be met to work with asbestos, but what you're seeing here in the video happens to be a cast iron pipe that the expander head is just simply coming through, breaking that pipe apart, and pushing it into the surrounding soil. So corrugated metal pipe and ductile iron pipe are both on the developmental phase. Now, ductile iron pipe will fail in a different fashion from cast in the fact that it will want to return to its original shape. Cast, when it gets to its failure point, will fail just instantaneously. Ductile iron will actually elongate and stretch, and then it wants to come back out. Doesn't mean you can't burst ductile iron. It's just there's risks involved, and your contractor is going to have to make that determination. Job site setup. This is exactly how it is. 85% less trench, as we're seeing a receiving pit in this left picture. Pipe insertion pit is all the way on the other side. And then we look towards making as few connections in between as possible. Each of those connections, of course, has to be an excavation because we are manually connecting that pipe to whatever that connection is. Long term, that's what we want. We really don't want a grouted pipe connection like you would in CIPP. And pipe bursting for gravity sewers is Ruth had mentioned earlier, on a high slope condition, that grout was a weak point and pulled out. If we know that we have a sensitive joint with a manhole, we either go with a high-density polyethylene manhole, which is cool, or you can make sure that you further restrain that pipe through mechanical restraint or thrust block right at that specific high-slope scenarios we go through. There was a lot of discussion about chlorination, so we really don't have to go through this too much, but there's a process called pre-chlorinated pipe bursting that's safe and makes it so you can tie that pipe in right in the same day after you flush it out. So here's a couple more examples of that. Allowable bending radius, how forgiving it really is in order to be able to push this pipe through and install in that manner. So in tight neighborhoods, that's just a godsend to be able to make sure that we can get the pipe in. Most laydown yards that we're going to be looking for are going to be long and longitudinal, where we can have even as little as one employee fusing up all of your pipe beforehand, and the other employees can be out there doing restoration or third-party utility identification or other things of that nature as we go through. Then you'll pull that pipe into place. So it's 327. We're almost right there. Here's the engineering package. We did have a question about the engineering package. We were hoping for an update in 2022, but got slammed with lots of great questions and webinars and webinar offerings. We will have a revision to that 2023, which includes updated specifications for you, including slip lining, compressive fit slip lining, gravity sewer pipe bursting, all sorts of things for you, and some additional tools that PPI has handed out and created in the past couple of years for us as well. All of these things are available from the Alliance for PE Pipe, which is a nonprofit, of course. Pete, Dusty, if you guys want to come on, we'll have a couple of comments as well from what we've got. So we've got lots of things within that, connections, manholes, installations. These are standard details as we're looking at them. They are available to you both in AutoCAD format, PDF format, and the specifications are available both in PDF and Word format. We do want to talk about your polyethylene project. It's kind of what gets us going in the morning. We'd love to talk about high-density polyethylene. So feel free to contact us, tell us about your project, ask those questions, share some details about it. We love to see positive infrastructure. Prior to this gig, I was working at a municipality where I was replacing infrastructure at that municipality directly. So I love to see that you guys are out there doing the same thing for your municipality, and it truly makes us happy. Any closing comments?
Great job, Alan Ambler. Dan Landy, could you come on and tell everybody how to answer the question and how to get their PDHs, please? Thank you, Dusty. Thank you, Matt.
Yeah, so just stay on the line. As soon as you guys exit the chat, we stop the conversation. There's going to be a survey, just a few questions about what you guys are working on. But please leave your contact info. It's the most efficient and quickest way for us to get you those PDHs. And go ahead and request any information. We've mentioned a lot of resources throughout. So if you want to put any specific requests in there for follow-up, answer the questions, and we'll get that out to you as soon as possible. Great job today, everybody.
Yeah, thank you, everybody. And my goodness, to all our guests, thank you for staying on the call and listening and learning about polyethylene. We're going to see over 100 of you again tomorrow, same time, same station. We'll see you then.